Let's have a look at some specific frequencies here and what could happen if we change the frequency. What does it do to the wavelength? So here we've got a 256 Hz note. You can see it on the display there. And as we increase the frequency, I might scroll and do this a bit quite faster there. As you increase the frequency, you should be able to hear the high-pitched note occurring, and the waves they'll be closing up closer together because the wavelength's getting shorter and shorter. Or you can drop it down, go to a lower pitch note, and the waves will spread out. So you can see there's definitely a relationship between the frequency and the wavelength there. So what we're saying here is there is a relationship between frequency and wavelength. It turns out as the frequency goes up and it gets higher, the wavelength gets shorter. And because of that sort of relationship, we assume that it's not directly proportional, it must be inversely proportional to wavelength. If you went twice the frequency, I'd expect to get half the wavelength and vice versa. Okay? So there's an inverse relationship. And that should make sense from the formula, because if you look at this here, V equals F lambda. For a wave at a fixed speed, if you go to higher frequencies, you must be going to lower wavelengths to keep the speed the same. Okay? So if you're looking at that there, if you doubled the frequency, we would expect to get half the wavelength there to keep that speed the same. So that's where sort of, I guess, confirmation of that formula comes from, that idea that there is definitely an inverse relationship between the two. So let's start to look at some other things in terms of frequency. There's a thing called the Doppler Effect, which is the apparent change in frequency due to motion. So in terms of this here, if you imagine you had a bug on the surface of the water rippling or moving, as it's sort of struggling there, it'll actually send out some waves there. Let's imagine it stays stationary to start with though. The waves in all directions then would sort of arrive to each other at the same rate. So let's say we counted 10 waves in 2 seconds here. That would give you a frequency of 5 Hz. How frequently are the waves arriving? Well, they're arriving roughly 5 every second. Okay, so the frequency there will be 5. And we would expect the same sort of amount to come down here. That's 5, up there is 5, and at the back is 5. So that's if it's stationary. The frequency in all directions for all observers would be the same. They would receive the waves the same frequency. Now, so we're going to swim to the side here with a velocity of v. All right. So as it does so, the circle of the waves that it's sending out will be closer to one side than it was the other, because it's going to catch up to them. So if we look at this one here, and clone that one there, clone that. That circle he's sending out is going to start to catch up to the side that he's moving in that direction to. So this side here is closer to than he was before. If you clone another one here, the same thing is going to happen, where again it's closer to that side. I'm cloning that last one, and same with the last one. So for the last one, you'll find it's doing that as well. So what you're getting happening here is you're getting a bunching up of the waves here at the front. So the waves bunch up. And you should find, if you're watching from this position here, that they're going to arrive more frequently because they're coming in closer together. So you'll find there's a higher frequency at the front here. So instead of being 5 Hz, let's just say it actually rises up and it just makes it 6 Hz there. It's just a little bit closer together than it was before, and so it appears that the frequency is 6 Hz now because 6 waves are coming in per second on average. At the back here though, the frequency is going to do what? You can see these waves here are now spreading out at the back, because after the bug has sent the wave out, the next wave is sent out further away because the bug's been further away when it actually releases it. So this frequency is going to be lower, whereas that one's going to be larger. So let's say if it goes up by 1 at the front, it might go down by 1 at the back, and so instead of 5 Hz, you'll effectively have your 4 Hz there. And here on the sides, it'll essentially say pretty much about the same there, by the way. But at the front, it's going to give you a significant change. It's going to go up. At the back, it's going to go down. Now, in terms of pitch then for a sound, then you're going to get a high pitch note at the front where the object's approaching you, like a fire engine or something with its bell going, whereas it goes past you, you're going to get a low pitch note, and we can see that effect. So this effect is known as the Doppler effect, and it's the apparent change in frequency because it just appears to change frequency because of the waves being squashed up as they come towards you. And it's due to motion between either the source of the waves or the receiver. So you could actually drive towards a stationary note and get an increase in the pitch, or you can have that note come towards you because the source is coming towards you. And the frequency is going to go up if it's coming towards you, as I've just said. If it's going away from you though, you'll find it's going to go down. So this is if it's stationary, the frequency stays the same, but in the case where it's moving towards you, you're going to get a higher frequency at the front, where the waves catch up to each other, they bunch up to each other, and they're going to arrive more frequently, so a higher frequency. And at the back, we're going to get waves that are actually sort of spread out there, and the frequency is going to drop down lower. So you get that high-pitched note drop into a low-pitched note. You can also use this same effect as an astronomer. If stars are coming towards you, the frequency of their light waves will move towards the blue end, the high frequency end, and that's evidence it's coming towards you. But by and large, stars are going away from us, they're shifting down to the red end, and this is called a redshift, and it's evidence that the universe is expanding and moving away from us. You can do a similar thing here with, radio waves. If a radio wave was sent to a car like that, fairly spread out, as the car approaches you then, and the waves reflect off the car here, you'll find they reflect back much closer together when the car is moving towards you, because there's a frequency change here because of this actually bouncing it back. And the difference in frequency here, between the low frequency and the higher frequency, can be used to work out how fast the car is going, which you can use in police radars and so on. Okay, thanks.